I'm working through the acids and bases section in the 2019 chemistry paper, which starts with question 7, or question 1.7, which is a multiple choice question on acids and bases, and reads as follows. A hydrochloric acid solution and an acetic acid solution of equal concentrations are compared. How do the hydronium ion concentration of HCl and the pH of HCl compare with that of acetic acid? And what we need to remember here is that hydrochloric acid is a strong acid. We know that it is a strong acid because it ionizes completely when placed in water, whereas an acetic acid is a weak acid, which means it does not ionize completely in water. What that tells us is that the strong acid will always produce a higher concentration of hydronium ions, which means our options are either A or B, and stronger acids have lower pHs, as we remember that stronger pHs are closer to 0. And so the correct answer here is that the hydronium ion concentration in HCl is higher than that of acetic acid, and the pH is lower. So the correct answer to 1.7 is option B. Question 7 is always the question that relates to acids and bases in this exam, and question 7 reads as follows. A hydrogen bromide solution, HBr, reacts with water according to the following balanced chemical equation. The Ka value for hydrogen bromide is at 25 degrees Celsius is 1 times 10 to the power of 9. Question 7.1. Is hydrogen bromide a strong acid or a weak acid? Give a reason for the answer. And we can very clearly see here, we need to be reminded that our Ka value is always going to be the product of the hydronium ion concentration and the bromine ion concentration over the hydrogen bromide concentration. And so the fact that this Ka value is so much bigger than 1 tells us that the concentration of hydronium is far greater than the concentration of hydrogen bromide, which tells us that hydrogen bromide must be a strong acid. We say that hydrogen bromide is a strong acid, and our reason is because Ka is so much greater than 1, which tells us that HBr ionizes completely in water. Question 7.2. Write down the formulae of the two bases in the above reaction. And so we can see in this reaction hydrogen bromide is an acid, and it must be reacting with water, which we know is an ampholyte, but in this case is acting as a base because it is accepting a proton to become hydronium. So it is a proton acceptor, which makes H2O a base. And then what that then creates is bromine as a conjugate base because it has now lost the hydrogen ion, which means that it is, theoretically at least, willing to accept a hydrogen ion from hydronium, which is the conjugate acid of this base. So our second base is then Br minus. Question 7.3.1 reads, HBr reacts with zinc hydroxide according to the following balanced equation. An unknown quantity of zinc hydroxide is reacted with 90 cubic centimeters of hydrogen bromide in a flask. Assume that the volume of the solution does not change during the reaction. The excess HBr is then neutralized by 16.5 cubic centimeters of sodium hydroxide of concentration 0.5 moles per cubic decimeter. The balanced equation for this reaction is. This kind of question is very common in acids and bases, and I find that it is always better to picture this as two separate reactions. The first reaction is the reaction that occurs between zinc hydroxide, where we are told that it is an unknown quantity that reacts with hydrogen bromide. We also at this point do not know what the concentration or quantity of hydrogen bromide is. What we do know, however, is that the zinc hydroxide is the limiting reactant. It is the limiting reactant because we are told that the hydrogen bromide is in excess at the end of this reaction. So we're reacting a fixed amount of zinc hydroxide with more hydrogen bromide, which means that we are then left with a solution. Now note I'm drawing a second beaker here, although this technically is still the same beaker, but this beaker now only has hydrogen bromide that remains in it. Then we have also been told that this is a 90 cubic centimeter container or amount of substance in this reaction. We are then told in the second step, so this is step 1, the reaction between zinc hydroxide and hydrogen bromide. In the second step, we are told that the excess hydrogen bromide, the remaining hydrogen bromide from that first reaction, is now reacted with sodium hydroxide. Now this you can see, or you should see, resembles a titration, because here we know the exact concentration and volume of the sodium hydroxide that is added here, and we know that the number of moles of sodium hydroxide, number of moles of the base, is exactly equal to the number of moles of the acid, because they have used this word neutralized. They say that the excess HBr is neutralized with the sodium hydroxide, which tells us that they have added exactly the same amount of base as there is acid present here. And then also it's useful for us to know that hydrogen bromide is a strong acid, as we determined in question 7.1, and we know obviously that sodium hydroxide is a strong base. So what we are going to be trying to do in this question is we are going to use the amount of sodium hydroxide that is known to determine how much hydrogen bromide was left over. Because if we know how much hydrogen bromide was left over, we can determine how much of it must have reacted with the initial amount of zinc hydroxide. So question 7.3.1 reads, calculate the pH of the HBr solution remaining in the flask after the reaction with zinc hydroxide. So they're now saying once the amount of zinc hydroxide has completely reacted, has been used up, there's a certain amount of hydrogen bromide that remains, and we want to know what that concentration is, because we can use that to calculate the pH. So we start by performing the only calculation that we can, and that is to determine how many moles of sodium hydroxide we had to add to that HBr to neutralize it. And we can do that by saying number of moles of sodium hydroxide is equal to the concentration thereof multiplied by the volume. Concentration of sodium hydroxide given as 0.5 moles per cubic decimeter. The volume given as 16.5 cubic centimeters, but we know that that must be converted into cubic decimeters, and we convert cubic centimeters into cubic decimeters by dividing by 1000, which tells us that the actual volume for this calculation is 0.0165 cubic decimeters, which means that the amount of sodium hydroxide that was present, the number of moles, or the number of moles that reacted, was 0.0825 moles. Now once again, because they have used this word neutralize, and because we can also see that the ratio in which sodium hydroxide reacts with hydrogen bromide is 1:1, the ratio of sodium hydroxide to hydrogen bromide is 1:1, what that tells us is the fact that we had to use 0.00825 moles of sodium hydroxide means that there must have been 0.0825 moles of hydrogen bromide. Now, once we know how many moles of hydrogen bromide there are, we need to convert that into a concentration, because we need the concentration in order to determine the pH. And so we would say the concentration of hydrogen bromide is equal to the number of moles divided by the volume of that flask. The number of moles, as we've just calculated, 0.0825, and that is divided by the volume. We were told that it is 90 cubic centimeters, and we are told that that volume does not change throughout this reaction. So that, again, converted to cubic decimeters, dividing by 1000, is 0.09 cubic decimeters, which tells us then that the concentration of hydrogen bromide must be 0.092 moles per cubic decimeter. Now, we remember from the definition of a strong acid that the fact that hydrogen bromide ionizes completely in water, or that it is defined as a strong acid, means that the concentration of hydrogen bromide will be equal to the concentration of hydronium ions. So it's not necessary to show this, but I'm just explaining that now that we know that the concentration of hydrogen bromide is 0.092, and we know that it is a strong acid, that automatically tells us that the concentration of hydronium will also be 0.092. And we can end this calculation by saying, therefore, the pH of the solution is the negative log of the hydronium ion concentration. Negative log of the hydronium ion concentration, this formula is given in the formula sheet. Negative log of that 0.092. And that tells us that the pH of this solution is 1.04. The pH does obviously not have units. There are other ways to have solved this question. If you are comfortable using the formula, number of moles of acid over the number of moles of base is equal to the concentration of acid multiplied by the volume of acid divided by the concentration of base multiplied by the volume of the base, then you are welcome to use that. That would also get you to the concentration of the acid, which you would then substitute in here. The result would be exactly the same. Question 7.3.2. Calculate the mass of zinc hydroxide initially present in the flask if the initial concentration of hydrogen bromide was 0.45 moles per cubic decimeter. Now, we already know how many moles of hydrogen bromide were present after this reaction. And with this information, the initial concentration of hydrogen bromide, we can now calculate how many moles of hydrogen bromide were present at the start of this reaction, and then by subtracting those two, we can find the amount that must have reacted with zinc hydroxide. So we have been told that the initial concentration of hydrogen bromide was 0.045, so we can use the formula N is equal to C times V to calculate the initial number of moles, concentration given as 0.045, and that volume, once again, we were told that the volume remains constant throughout, 0.09, and that means that initially we had 0.0405 moles of hydrogen bromide present. Now, since we know that at the start there were 0.0405 moles of hydrogen bromide, and after this reaction, we worked out in the previous question there were 0.00825 moles of hydrogen bromide present, we can then calculate the number of moles of HBr that reacted. We can do this by saying it is the initial number of moles minus the final number of moles. The initial number of moles, as we've just calculated, 0.0405, minus the final number of moles, 0.00825, which tells us that we must have reacted 0.03224 moles of hydrogen bromide. What we can now do is we can see that hydrogen bromide reacts with zinc hydroxide in a ratio of 2 to 1, which means that for every 2 moles of hydrogen bromide that are required, we require only 1 mole of zinc hydroxide. This is taken from the balanced equation over here. And so, since we know that 0.03224 moles of hydrogen bromide were used, we can calculate half of that to see exactly how many moles of zinc hydroxide must have been present, and that is 0.016125 moles of zinc hydroxide. Now we finally have the number of moles of zinc hydroxide, and so we can say the number of moles of zinc hydroxide is equal to the mass of zinc hydroxide over the molar mass. Number of moles is our known quantity, 0.01625. Mass is the unknown, and the molar mass for zinc hydroxide is 99 grams per mole, which therefore tells us that we must have started with 1.596 grams of zinc hydroxide. Just to walk through that once again, this type of question is very common where there is an initial reaction in which one of the excesses remains. The excess is usually or is always going to be an acid or a base. That excess is then neutralized. That is what's happening in stage 2 here. So we started with hydrogen bromide and zinc hydroxide. We reacted those completely. The zinc hydroxide was then used up, and we were left with excess HBr. To determine how much of that acid remained, we performed a neutralization reaction or a titration in which we neutralized it with a base. And since we know the exact quantity of the base, the exact amount of sodium hydroxide that was added, we can then determine how much hydrogen bromide, how much of that excess remained at the end of the reaction. Then, since we know how much remained at the end of that reaction, we can calculate the amount that reacted in that reaction, and with that amount we can see how it reacted with that initial quantity of zinc hydroxide and then determine the mass as requested.